Right now, behind the pristine white drywall of your laundry room, there is a slow motion chemical war happening.
Oh, absolutely. It's happening right under our noses.
Yeah, and we look at a freshly renovated room, we see that crisp paint and the neat little plastic box where the washing machine hoses plug in, and we just assume the system is simple, calm, modern.
Right, because that's all you can see.
Exactly. But if you were to peel back that drywall, you wouldn't see calm. You would see a tightly constrained, highly volatile ecosystem.
The contrast between the surface and what lies beneath is staggering,
Mhm.
honestly. People assume plumbing is just, tubes carrying water.
Like a basic straw or something.
Yeah, like a straw. But anyone looking to upgrade their own home quickly realizes that the hidden world behind the drywall is where all the actual engineering takes place.
And it's not a lot of space either.
No, not at all. It is a puzzle involving chemistry, thermodynamics, and fluid dynamics, all crammed into a space that is only about 3.5 inches deep.
Which is wild. And that is exactly our mission for this deep dive today. We are opening up the walls for you.
Yes, we are. We're getting right into the details.
We're exploring the notes and instructional videos of plumbing expert Claude Taylor. He painstakingly documents the process of upgrading a dated 40-year-old laundry standpipe to one of those sleek, modern laundry boxes.
And we are looking at the specific techniques required to navigate this environment. Because upgrading this hardware isn't just about making things look tidy for the drywallers.
Right, it's not just cosmetic. It's kind of like swapping out an old clunky flip phone for a sleek smartphone, right?
That is a perfect analogy, yeah.
It's not just about looks. It's about modern functionality and, honestly, protecting the house's operating system.
Exactly. You have to safely merge 40-year-old degraded materials with modern synthetics. And you have to do it without destroying the rest of the house in the process.
Okay, let's unpack this. Because my first thought when looking at a plumbing upgrade is that it's just about replacing an old part with a new one.
Right, just unscrew the old, screw on the new.
Yeah, like swapping out a battery. But seeing Claude work, it feels a lot more like building a ship inside a bottle. You have this tiny constrained opening.
And every single movement you make has massive consequences.
Yes. Which brings us to the very first step of the project, the tear out.
Dismantling the old system is often more dangerous than building the new one, frankly.
Mm.
In the instructional material, we're dealing with old galvanized steel water pipes.
And you notice immediately that Claude doesn't just grab a wrench and start violently twisting things off.
No, he is incredibly methodical. He uses 2 sets of heavy channel locks simultaneously.
I saw that. He clamps one heavy wrench onto the pipe, extending from the floor to hold it completely rigid, and then he uses the second wrench to turn the fitting he actually wants to remove.
Right.
But why go through the hassle of awkwardly operating 2 heavy tools in such a tiny space?
It comes down to torque and the butterfly effect of a home's plumbing.
The butterfly effect.
Yeah, so if you just clamp onto a pipe and start cranking, that twisting force doesn't just stop at the fitting, it travels.
Oh, wow.
It travels down the entire length of the pipe, right down into the floor joists and through the wall.
So you could be working in the laundry room, and the torque you apply ends up, like, cracking a brittle 40-year-old threaded seal under the kitchen sink 3 rooms away.
Precisely. You fix a cosmetic issue in the laundry room, but you create a catastrophic leak inside a distant wall cavity.
That sounds like a nightmare.
It is. So holding the lower pipe perfectly still isolates the force. It basically creates a quarantine zone for the mechanical stress.
Makes sense.
Ah.
And as he carefully removes these old steel fittings, he operates under a fundamental, non-negotiable rule of modern plumbing.
Hot water is always on the left.
And cold water is always on the right,
Oh.
which is something we all intuitively know from, turning on a faucet.
Right, you reach for the left for hot without even thinking.
Exactly. But I never really thought about why it's so rigidly enforced behind the walls.
Well, it was standardized primarily for safety, specifically for the visually impaired, or, honestly, simply for anyone reaching blindly into a shower enclosure.
Oh, sure.
If the layout was random in every house, people would constantly be scalding themselves. The infrastructure has to be universally predictable.
That makes total sense. Now, once those old steel fittings are finally off, Claude is ready to run brand new copper piping up to the new modern laundry box.
Yes.
But the main pipes coming up from the floor are still that old galvanized steel. Wait, mixing metals, isn't that a bad idea?
Oh, it is a very bad idea.
Like putting 2 fiercely rival sports fans in the same cramped room.
What's fascinating here is that treating different metals as if they are the same material is the #1 way to completely destroy a home's plumbing.
So they really do fight each other.
They will absolutely start a chemical war.
Yeah.
And the process is called galvanic corrosion, or electrolysis.
Electrolysis. I remember the term from high school chemistry, but seeing it applied inside the walls of a house feels so abstract.
It does, yeah.
How does simply touching two metals together cause damage? They're just sitting there.
Think of it like building a slow-motion battery inside your wall.
Okay, a battery.
Yeah. For a battery to work, you need two dissimilar metals, an anode and a cathode and an electrolyte, to facilitate the transfer of electrons between them.
Right.
When you physically thread a copper pipe directly into a galvanized steel pipe, you have your two dissimilar metals.
And the water flowing through them acts as the electrolyte.
Exactly. The water completes the circuit. A very real, low-voltage electrical current actually starts flowing between the copper and the steel.
Wow.
This electrochemical reaction causes the molecules of one metal to basically jump ship.
And the crazy part of the notes is that it's often the expensive, highly durable copper that takes the hit and corrodes prematurely.
It is. People think they're doing a good thing by upgrading to copper.
You think you're giving your home a premium upgrade, but by connecting them directly, you're setting a ticking time bomb for a massive leak.
Which is why Claude utilizes a very specific piece of engineering. It's called a dielectric union.
A dielectric union. It looks just like a standard brass plumbing fitting from the outside, right?
It really does. But it acts as a chemical peacekeeper.
So what is actually happening on the inside of it?
Inside, it features a specialized, high-density plastic insert. That plastic acts as an impenetrable physical barrier, ensuring the copper and the steel never actually touch each other.
Oh, I see.
And then a black rubber gasket is compressed between the two sides when you tighten it down.
So the water can still flow freely between the two pipes, but the electrical circuit is permanently broken because the metals are physically isolated.
That is the magic of the dielectric union. Without that small $5 component, the entire multi-thousand-dollar upgrade would eat itself alive in a matter of years.
All over $5. That's incredible.
It really is. And speaking of old pipes failing, the source material highlights a very counterintuitive fact about those old galvanized steel pipes.
Right, because we typically think of steel as failing because it rusts through from the outside, like an old car left in a field.
Sure, yeah.
But in a 40-year-old house, Claude notes you often have to replace them for a completely different, totally invisible reason.
Calcium buildup.
Just from the water.
Yeah. Over 4 decades, the dissolved minerals in the municipal water supply slowly precipitate out, and they coat the inside walls of those steel pipes.
It's basically clogged arteries for your house.
That is a highly accurate comparison. The heavy texture of galvanized steel gives the calcium a perfect surface to grip onto. Layer by layer, year after year, it builds up.
So it's shrinking the pipe from the inside.
Exactly. A steel pipe that looks perfectly fine on the outside, a full inch thick, might only have a tiny pinhole-sized opening left in the center for the water to squeeze through.
Which means you lose all your water pressure to your washing machine. And not because the pipe broke, but because it choked itself off from the inside.
Right. Now, we've solved the problem of getting highly pressurized water into the washing machine using properly isolated metals.
Yes, the water is in safely.
The water has to come in, and it also has to go out.
And that fundamentally changes the physics of what we are doing. We've solved the pressurized water, so the conversation logically transitions to getting gravity-fed wastewater out.
And that takes us completely out of the world of metal and down into the world of plastics.
This is where we encounter the next major transition problem. The old waste pipe coming out of the floor in this specific wall is ABS.
Right, the black plastic.
Yeah, that thick black plastic piping, common in older homes. But the modern standard that the new laundry box requires is PVC.
Which is the white plastic piping you see piled high at every hardware store.
Here's where it gets really interesting, because as a casual DIYer, you look at this situation and think, okay, they are both just unpressurized plastic tubes.
They look like they should just fit together.
Exactly. Why overcomplicate this? Why not just grab a can of that heavy-duty plumbing glue, slather it on the white pipe, stick it into the black pipe, and call it a day?
This raises an important question about what plumbing glue actually is.
Yeah.
Because the industry term is actually solvent cement.
Solvent cement.
Yeah, and it functions very differently than the adhesive glues we use in daily life.
So it's not just a sticky paste that dries hard?
Not at all. Standard glue creates a topical adhesive bond. It just sticks two surfaces together. Solvent cement, though, creates a cohesive bond.
Meaning it changes the material?
Yes. It chemically attacks the top layer of the plastic. It literally melts the polymer chains.
Oh, wow.
When you push the two softened pipes together and the solvent evaporates, the plastics harden back up. The two separate pipes literally fuse into one single continuous piece of material.
So it's a chemical weld.
It is a chemical weld.
But if they both melt, why can't you solvent weld the white PVC to the black ABS? I mean, melting is melting, right?
Because they have completely different chemical structures, they melt at different rates, and their polymer chains don't interlock properly.
Ah, so they won't grip each other.
Right. If you try to solvent weld them together, you might get a joint that looks structurally sound to the naked eye, but it is incredibly brittle.
And a washing machine draining isn't exactly a gentle process.
Not at all.
It's aggressively dumping gallons of hot, soapy water down that pipe, creating massive temperature swings and vibrations.
Exactly. And eventually, that brittle chemical joint will snap, and it will dump all that dirty water directly inside your sealed wall.
Which is why the plumbing codes strictly forbid chemical welds between ABS and PVC.
Yes. You must transition them mechanically, and for that, Claude uses a no-hub connector.
A no-hub connector. I was looking at that in the source material. It seems remarkably simple compared to the chemistry we just talked about.
It is very simple.
It's just a thick, durable rubber sleeve that bridges the gap between the black pipe and the white pipe, surrounded by a ribbed stainless steel shield with metal bands.
It acts as the mechanical equivalent of our dielectric union. You slide the rubber over both plastics, take a wrench, and torque down the metal bands.
So the metal bands squeeze the rubber tight.
Right. The steel shield distributes the pressure evenly, compressing the rubber so tightly around the inconsistent plastics that it creates an absolute leak-proof, vibration-absorbing seal.
But before Claude could slide that rubber no-hub onto the old black ABS pipe, he had to cut the pipe down to size inside the wall.
Yes, the tear-out continues.
And the notes document a moment here that is such a visceral lesson in physics. Claude attempts to use a cutting cord, but it completely backfires. What exactly went wrong there?
The cutting cord incident is a brilliant example of thermodynamics working against you.
Okay, set the scene for us.
Well, a cutting cord is a braided wire covered in abrasive teeth. You wrap it around the back of a pipe in a tight space, grab the two handles, and pull it back and forth rapidly.
Like a bow drill.
Exactly, like starting a fire. It removes material through sheer friction.
Right, which sounds perfect when you can't fit a bulky saw inside a tight wall cavity.
Usually it is.
Yeah.
But ABS plastic has a relatively low melting point.
Oh, no.
Yeah. As Claude aggressively pulled the cord back and forth, he generated massive amounts of heat. The physics of the friction generated thermal energy much faster than the abrasive teeth could remove the material.
So instead of turning the plastic into dust, he just melted it into a liquid?
He did. The cord cut all the way through, but the molten ABS at the top of the cut simply flowed back together behind the wire.
Wait, really? It just healed itself?
Literally. By the time he finished the cut, the pipe had cooled and completely fused itself back into a single solid piece. He effectively welded the pipe back together in his attempt to cut it in half.
That is hilarious. He had to completely abandon the cord, grab a tiny little handsaw, and manually slowly cut through it the old-fashioned way.
It is a stark reminder that textbook theory doesn't always survive real-world application.
Absolutely. But once that battle is won and the mechanical no-hub connector is secured, the stage is finally set.
Everything is prepped.
The pressurized water lines are chemically isolated and safe. The gravity waste lines are mechanically transitioned. Now it is time to connect the brain of the whole operation, the modern laundry box itself.
And these boxes are remarkably clever in their design.
They really are. When you look at one, it's just a hollow square of durable plastic with 3 large holes punched in the bottom. But the beauty is its sheer adaptability.
It is engineered to accommodate whatever chaotic framing or plumbing situation you uncover behind your drywall.
Like, Claude sets his up so the hot and cold water valves sit in the 2 outside holes, and the large 2-inch drain pipe for the wastewater sits in the far right hole.
Right.
But if a massive floor joist was blocking the right side, he could easily pop the drain into the left hole instead.
Or he could even take the entire box, flip it completely upside down, and have the water lines drop in from the ceiling while the drain drops to the floor.
It gives you total freedom to navigate the physical constraints of the house.
Which is huge when you're dealing with older homes.
So what does this all mean for the final installation? Because Claude's next move seems entirely counterintuitive.
The prefabbing?
Yeah. He measures the distances inside the wall, but then he takes all his fresh copper piping, his elbow fittings, his valves, And he walks out into the middle of the room.
Yep.
He lays them all on the floor and starts building and soldering the entire assembly out in the open. Isn't that creating double the work? Why piece it together on the floor just to have to put it back into the wall?
If we connect this to the bigger picture, this technique called prefabbing is arguably the most critical safety lesson in the entire deep dive.
Really, safety.
Yes, prefabbing is fundamentally about mitigating fire risk.
Because to join copper pipes, you have to solder them.
Consider the mechanics of soldering. You're using a propane or MAPP gas blowtorch that burns at nearly 3,600 degrees Fahrenheit.
That is intensely hot.
You have to apply that open, roaring flame directly to the copper fittings until the metal reaches roughly 400 to 500 degrees. Only then is it hot enough to melt a solid wire of metal alloy.
The solder.
Right. So that capillary action can suck the liquid metal up into the joint against gravity.
And doing that inside a wall cavity is basically asking for a disaster.
It is incredibly dangerous. The space between the studs is a 40-year-old wooden tinderbox.
Yeah.
You are firing a blowtorch an inch away from dry, splintered wood, highly flammable paperback drywall, and decades of dust and cobwebs.
That's terrifying when you put it like that.
Plumbers accidentally burn houses down. It is the statistical reality of the trade.
So by prefabbing the assembly out on the floor, Claude creates a quarantine zone for the fire hazard.
Exactly.
He builds the entire complex network of valves and elbows where there is zero risk of igniting the structure.
He does all the heavy, dangerous lifting in an open environment. Then he takes this pre-built solid unit, slides it into the wall, and connects it to the main lines.
Instead of making 6 or 7 highly dangerous solder joints blind inside the wall, he only has to make 1 or 2.
It drastically reduces the risk.
And even for those unavoidable joints inside the wall, he employs a few highly granular pro tips. The first thing he does is grab a cheap plastic spray bottle full of tap water.
Oh, this is a great trick.
He aggressively mists down the wooden studs and the drywall backing behind the pipe. It is such a simple, incredibly cheap insurance policy against a stray spark catching a cobweb.
The preparation is meticulous. And it's during this final soldering phase inside the wall that we see him use the egg-shaped trick.
Yes, I saw him do this and had to reread the notes to understand it.
It's brilliant.
He has a perfectly round copper pipe and a perfectly round elbow fitting. But before he applies any solder, he takes his heavy pliers and deliberately squeezes the end of the straight copper pipe to slightly deform it.
Yep.
Why intentionally damage a brand new pipe?
Because he is manipulating the physical tolerances of the materials to fight gravity.
Wait, how does it fight gravity?
Well, when you slip a perfectly round fitting over a perfectly round pipe, there is a tiny gap. That gap is necessary for capillary action to suck the molten solder in later.
Okay, I follow.
But before the solder is applied, that gap means the fitting is loose. If you let go of it, gravity will cause it to swing downward, ruining the specific angle you carefully measured.
Which is a massive problem when you only have 2 hands, one holding the blowtorch and the other holding the wire solder.
Exactly.
You don't have a third hand to hold the fitting in position.
By squeezing the pipe ever so slightly into an oval or egg shape, he creates a temporary friction fit.
Oh, I get it now.
When he forces the fitting over that oval, the metals bind against each other just enough to hold fitting rigidly in place at the exact required angle. It leaves both of his hands free to safely operate the torch and apply the solder.
It is a brilliant utilization of thermal expansion and physical friction. Another specific choice I noticed was his torch.
Oh, the auto start tip.
Yeah. He doesn't use a standard manual light torch. He uses a specific auto start propane tip. Why is that?
The ergonomics of the wall cavity demand it. With a standard torch, you turn on the gas, creating a cloud of flammable vapor, and then you use a clunky metal spark striker to ignite it.
Right. In an open room, that's fine.
But when your arm is crammed sideways between 2 wooden studs, trying not to burn your own elbow.
Yeah, you don't have the leverage or the physical clearance to be aggressively snapping a spark striker.
The auto start tip eliminates the danger. You position the unlit, cold torch exactly where you want it against the pipe. Only when you are perfectly aimed and your body is safely out of the way do you pull the trigger to instantly ignite the flame.
It is a massive upgrade in both efficiency and structural safety.
It really is.
And speaking of efficiency in tight spaces, his choice of a 6-way screwdriver during the final hookups is another prime example.
Oh yeah, that's a classic tool.
For you listening, a 6-way screwdriver looks standard, but the metal shaft pulls out and flips around, offering different bit sizes. But the real secret is that the hollow shaft itself acts as a nut driver. Why is that specific tool so critical here?
Think about the physical limitations we've been discussing. Space is at an absolute premium.
Right.
You cannot be wearing a bulky tool belt, constantly pulling your arm out of the wall cavity to blindly swap between a flathead for a bracket, a Phillips for a faceplate, and a wrench for a hose clamp on the no-hub connector.
It would just be exhausting and risky.
Exactly. Having one single handle that instantly adapts to every fastening mechanism means you maintain your focus. You keep your hands on the work and minimize clumsy movements that could disrupt the newly sealed joints.
The efficiency of movement is what finally brings the entire chaotic system together. The dielectric unions are safely bridging the chemical gap between the old steel and the new copper.
The no-hub connector is mechanically absorbing the vibration between the mismatched plastics.
The copper lines were safely prefabbed to protect the house from the torch.
And finally, he securely straps the entire assembly to the wooden framing. When that washing machine aggressively turns on, violently opening and closing its valves, the resulting water hammer effect won't cause the pipes to shake or rattle.
The system is completely locked down.
Completely.
It allows the drywallers to finally come in, put up their fresh whiteboard, paint it, and leave us with that calming, modern illusion of a simple laundry room.
And what we have to remember is that the underlying physics we explored today apply far beyond the laundry room.
Absolutely. The source material notes that you use these exact same principles when installing an ice maker box behind a refrigerator or, when you were upgrading the shutoff valves buried under a bathroom sink.
Preventing galvanic corrosion, understanding the chemical limits of plastics, and prioritizing fire safety through prefabbing. These are the non-negotiable rules for maintaining a home's operating system.
So, to everyone listening, the next time you look at that clean, white plastic laundry box set perfectly flush into the wall, we hope you see it a little differently.
You'll know the incredible amount of material science, thermodynamic management, and hidden engineering sitting just an inch behind that paint.
It really is a fascinating hidden world back there. And it leaves me thinking, if a simple, seemingly innocent connection between two common metals like copper and steel can silently destroy a home's plumbing from the inside out via electrolysis,
Yeah.
what other invisible chemical or physical battles are secretly being fought inside the structures of the homes we live in every single day?
That is a thought that will change how you look at the entire building around you.
We'll leave you to ponder that one. Thanks for joining us, and we'll catch you on the next deep dive.